Tonight's lesson is going to continue our discussion on thermodynamics. Right now we're in section 15.2 in the textbook if you want to follow along. We're going to continue to discuss that first question I posed in the last video. How do substances absorb and release heat? So we've already dealt with the case where if you have a hot piece of metal, you can calculate the heat absorbed or released by that metal if you know the mass of the metal, the amount it changes temperature, and the specific heat of the metal. Q equals mc delta T. But in this video, we're going to take that a step further, and hopefully by the end of it, you'll be able to answer the following question. If a 2.5 gram piece of copper metal is heated to 225 degrees Celsius and is then dropped into 50 grams of water at 35 degrees Celsius, how hot will the water get? So essentially, we know how to deal with the heat transfer of one object. Now we're going to deal with the heat transfer between two materials, between, in this case, the copper and the water. Before we solve this question, we have to deal with the question of thermal equilibrium. Now, thermal equilibrium is a very important concept for solving these kinds of questions. So we already have discussed how when you have a hot object and you have a cold object, heat is transferred from the hot object to the cold object. It always happens this way. You never have cold objects transferring heat to hot objects. It's always the hot object transfers heat to the cold object. Now, the concept of thermal equilibrium basically says that the hot object is going to transfer heat to the cold object until they're both the same temperature, okay? So if you drop a hot piece of copper into water, the copper is going to cool down, the water is going to heat up, and they're going to stop transferring heat when they both reach the same temperature. So that's an important concept to keep in mind as we solve this problem. So let's go back to the initial question. A 2.5 gram piece of copper is heated to 225 degrees Celsius. It's then added to a 50 grams of 35 degrees Celsius water in an insulated container. And how hot will the water get? So we want to start with the most universal claim, that first law of thermodynamics that says that Q of the universe, the total heat transferred to or from the universe, is 0 joules. That's another way of saying that the total energy of the universe is constant. You can't gain or lose energy when we're talking about the universe. Okay, so then remember I said you could break the universe into a system that we care about and surroundings that we aren't considering. So the system and the surroundings, if you add up the heats, it's 0 joules. So that means that whatever heat is gained by the system is lost by the surroundings, and whatever heat is gained by the surroundings is lost by the system. The total heat, the total thermal energy, is conserved in any of these processes. So if we want to consider copper as our system, so this is what we care about, this piece of copper. So if copper is our system, then whatever heat is lost by the copper is gained by everything else. So most of that heat is going to go from the copper into the water. But some of that heat is going to be transferred to the glass. If you drop a really hot piece of copper into a glass, the glass is going to get hot too. Some of that heat is going to go into the air. Some of that heat is going to go from the glass to the table. Okay, so whatever's lost by the copper is gained by everything else. And when I say everything else, I mean everything else. So it's going to be very hard to solve this problem if we have to think about the heat absorbed by the table, and the heat absorbed by the cup, and the heat absorbed by the water, and the heat absorbed by the air, and the heat absorbed by these pliers. I mean, that's just a lot to keep track of. So if only there were an easier way of doing this kind of problem. Well, as a matter of fact, there is. It's called coffee cup calorimetry. If we modify the way we do this experiment, we can make this calculation a lot simpler. So, instead of putting my water in a glass container, what if I put it in a very thick styrofoam cup? And then I put that very thick styrofoam cup in another very thick styrofoam cup. And then I covered it with the thick styrofoam lid. And then I made little holes for my thermometer so I could tell the temperature, and a little hole for the stirrer so I could stir the water around. Well, that would prevent any heat transfer to anything except the water. So I initially said that the heat of the copper plus the heat of the surroundings is 0 joules. But in an insulated container, the heat of the surroundings is basically just the heat of the water, because no heat is escaping to the cup, no heat is escaping to the outside. So then I end up with saying the heat of the copper plus the heat of the water is 0 joules. Well, now this problem has become a lot easier. I can analyze the heat of the copper, and I can analyze the heat of the water, and I don't have to worry about the cup. I don't have to worry about the table. I don't have to worry about the air. So that I just made this problem a whole lot easier. So, again, a 2.5 gram piece of copper metal is heated to 225 degrees Celsius, and it's then added to 50 grams of 35 degrees Celsius water in an insulated container, and they want to know how hot the water is going to get. So first off, I start with where I ended up with last slide. The heat of the copper plus the heat of the water is equal to 0 joules, and that's because we have an insulated container. So the only things we have to consider here are the copper and the water, because no heat is escaping outside of the water. So let's plug in our Q equals MCAT formula here. So the mass of the copper times the specific heat of the copper times the delta T of the copper plus the mass of the water times the specific heat of the water times the change in temperature of the water is 0 joules. Okay, so far so good. I can start plugging in numbers. But as you notice here, I now have 2 MCAT formulas because I'm dealing with 2 substances. So 2.50 grams is the mass of the copper, 0.386 joules per gram times degrees Celsius, as we can see from this table. Well, the table says 0.385, but that last digit's a guess. I got it from another table, full disclosure. But anyway, that's the specific heat of the copper times delta T of the copper is equal to 50.0 grams is the mass of the water, 4.18 is the specific heat of the water, and then times delta T of the water is 0 joules. Now you might be wondering why I didn't plug in 225 degrees Celsius for delta T of the copper and 35 degrees Celsius for the temperature of the water. The reason is that delta T is not the same thing as T. Delta T is the change in temperature. Now, the copper metal didn't change its temperature by 225 degrees. The water didn't change its temperature by 35 degrees. That's the temperature that we started out with. Okay, so anytime you have a delta, that means a change in. That doesn't mean the temperature at a given time. So to calculate the change in temperature, delta temperature, we're going to subtract the initial temperature from the final temperature. That's the way we calculate the change in anything, right? If you want to figure out how much you grow, your change in height, you subtract your initial height from your final height, right? If you want to figure out how far you've traveled, you subtract your initial position from your final position. So it's the same thing with temperature. If you want to know the change in temperature, you calculate, or you figure out what the final temperature is, you figure out what the initial temperature is, and then you subtract the two numbers. So just before I substitute in this formula, let's just do a little cleaning up here. So if you multiply 2.5 times 0.386, you get 0.965 joules per degree Celsius. As you can see here, the grams cancel out, so I don't need that unit anymore. Grams divided by grams is 1. And likewise, grams divided by grams is 1. And if I multiply 50 times 4.18, I'm going to get 209 joules per degree Celsius. Now, before I start plugging values in for the change in temperature, let me just show you something. So, I have joules here per degree Celsius, joules per degree Celsius, and on this side I have joules. So in order to make the units the same at both sides, the temperature, the delta T, has to be in units of degrees Celsius. So just keep that in mind, that that's going to be our final unit. Because right now, I'm going to get rid of the units just to make things look a little neater. So, I got rid of the units, but I also substituted in the delta T equation here. So, 0.965 times delta T, which is the final temperature of the copper, minus the initial temperature of the copper when it's dropped in the water, because when it's 225 degrees, that is when it's dropped in the water. And then 209 times the final temperature of the water, whatever that is, minus 35 degrees Celsius, which is the initial temperature of the water before the copper is dropped in. So get excited. We are just at our home stretch right now. Just copying that information from the past slide. Now we have an equation. Now this is unfortunately an equation that we can't solve because the final temperature of the copper is one variable and the final temperature of the water is another variable. So you actually can't solve an equation with two variables. You can never get one variable equals a number if you've got two variables in your equation. So wouldn't it be nice if we could get rid of one of these variables? Well, as a matter of fact, we can get rid of one of these variables using the concept of thermal equilibrium I told you about earlier. So remember, thermal equilibrium says that if I have a hot object and I have a cold object, the hot object is going to transfer heat to the cold object until they both reach the same temperature, right? Okay, so if that's true, then the final temperature of the copper is going to equal the final temperature of the water. The two are going to be the same number at the end of the day because the copper is going to be transferring heat to the water until they both reach the same temperature. So I'm going to call that temperature that they both reach TF for T final temperature. And now let's substitute TF into our equation. All right. So now I have only one variable that I've got to solve for. So from now here on out, it's just a matter of algebra. So the first thing I'm going to do is move this term to the other side of the equation by subtracting it. So I wrote 0.965 times TF minus 225 is 209 times quantity 35 minus TF. So rather than put the negative sign out front, I flipped the sign of these two terms, which is the equivalent thing, and that means I have less negative signs to keep track of. So that's why I did that. So then I'm going to divide both sides of this equation by 0.965, and I end up with TF minus 225 is 217 times 35 minus TF. Now let me distribute the 217, and that's going to give me TF minus 225 is 7595 minus 217 times TF. And now let me just move the TFs to one side and the numbers to another. So 218 TF is 7820, and that means TF is 35.9 degrees Celsius, expressed to 3 sig figs, using that unit that I told you to keep in mind from earlier. All right, so that was a lot of work, wasn't it? Now, I consider my math skills pretty good, but I know the first time I did this problem, I made a couple of very stupid mistakes. So, in order to check our work, we got to see whether it makes sense. So let's kind of look at this problem just from a qualitative perspective and see if our numbers line up with what we'd expect to happen. So if you have your hot piece of copper is at 225 degrees Celsius, you have your cold water, and that is at 35 degrees Celsius. So my hot copper is going to transfer heat to my cold water. And so I should expect my final equilibrium temperature to be somewhere in between 225 and 35. And indeed it is. 35.9 is less than 225 and it's greater than 35. The other check I want to do is I have 2.5 grams of copper and 50 grams of water. The specific heat of copper is very low and the specific heat of water is very high. So those facts both mean, so I have a greater mass and a greater specific heat of water, so that means that it takes more energy to raise the temperature of water than it does to raise the temperature of copper. So I should expect the temperature of the copper, since it's a good conductor, to change a lot, and the temperature of the water not to change very much. And indeed, that's what I see. The temperature of the water only changed 0.9 degrees. The temperature of the copper changed by almost 200 degrees. So that should give you an idea of how good an insulator water is. That you can put something that is above the boiling point of water in what is essentially room temperature water, maybe a little over room temperature, and the temperature is only going to change by 0.9 degrees. All right, so let's see how you do on a practice problem here. So the question asks, what is the resulting temperature when 35 grams of water at 75 degrees Celsius is mixed with 15 grams of water at 15 degrees Celsius? Now the answer you get should be 57 degrees Celsius. But let's see. Just a couple hints here. First off, the heat absorbed by the cold water is equal to the heat released by the hot water. You should apply the Q equals MCAT equation. And then just remember that delta T is not a temperature, but a change in temperature. So you've got to substitute the final minus the initial temperature. The other thing you can do here is, because these are both samples of water, you can actually cross out the specific heat because it's the same on both sides. So you should just be able to plug your numbers in and you should be able to get 57 degrees Celsius. We'll discuss it in class if you don't, but good luck. And there's your chart.